A video lecture for section 2.5. This is infinite sets, and this is for MGF 1106, and my name is Jorge Gavillan. So the objectives for section 2.5, infinite sets, we're going to be able to recognize the difference between a finite and infinite sets. We're going to show that the set of natural numbers and the set of integers are countable. We're going to be able to show that the set of rational numbers is countable, and then we're going to give an example to show that not all infinite cardinal numbers are the same size. And so the first thing we're going to talk about is one-to-one correspondence. Two sets A and B are in one-to-one correspondence if we can pair the elements of the two sets so that every element of A is paired with exactly one element of B, and every element of B is paired with exactly one element of A. So for example, here we have set T, says set of famous tenors, is in a one-to-one correspondence with set F. So this is a set of popular female vocalists. Now, because we can pair each tenor in T with exactly one singer in F as follows, this set is a one-to-one. These two sets are in one-to-one correspondence. Now, infinite sets, a set of infinite is if we can place it in a one-to-one correspondence with a proper subset of itself. So note that a finite set cannot be placed in a one-to-one correspondence with any of its proper subsets, but an infinite set by definition can. And the reason being because a finite set has an upper limit of how many elements it has. And so if I take a subset of that, I, by definition, have already excluded some of the sets. And so there won't be a one-to-one pairing between those two. So we're going to show an example. The set of natural numbers is infinite. So we're going to show that the set of natural numbers is infinite. So here we have n. Let n be the natural numbers. Let e be the even integers. Then the following is a one-to-one correspondence between n and its proper subset e, which is the even integers. And you can see that if we're able to do this, like we do 1 and 2, 2 and 4, 3 and 6, there is a relationship where lowercase n denotes the element in the natural numbers, and then 2 times lowercase n denotes the element in the set of even integers. So instead of saying that the set of natural numbers is infinite, we can be more precise. Cantor called the cardinal number for the set of natural numbers Aleph null. This is the first letter of the Hebrew alphabet. So therefore we can write the cardinal number of the natural numbers as Aleph null. So any set that is either finite or that is in a one-to-one correspondence with the natural numbers and therefore has a cardinal number Aleph null is called a countable set. So we're going to show that I, the set of integers, can be put in a one-to-one correspondence with the set of natural numbers. So the solution here, the following matching shows the correspondence. So in the correspondence, we're assuming that n represents a positive integer. So as you can see, that we can actually put them in a one-to-one relationship. And so therefore, the cardinal number of I is a Aleph null, and I is in fact a countable set. So here's an example. We can see that there are sets with cardinal numbers that are greater than Aleph null. So first, for an example, illustrate the technique. So the question is, are there more chairs or more students? Do you have to count each to answer the question? And we know that there are more chairs because we see that there are chairs left over. So we don't really have to count the set, if you will. We can see if there are elements left over. And that's the end of 2.5. Thank you.